Hello, hello. Anyone, is it okay now? Is it audible? And then is the background noise lesser somehow? Anyone, write back if the audio check is going out good. Perfect. Then I will start with sharing my screen as well. Hello. Okay, perfect. Hmm. Okay, yeah. Yeah. So, hello everybody, and uh, good evening. Let's say, let's just assume that it's the later part of the evening instead of saying down a good night, which would mean a good night. So, I am Dr. Devdut Sheet from the Department of Electrical Engineering at IIT Kharagpur, and I work predominantly in the area of machine learning for medical image analysis and computational medical imaging. So I would be sharing down across on this talk a few of experiences which we had gathered down at our research group in Kharagpur in the area of trying to adapt different kind of deep neural networks between domains. So I would start with a very basic ideological paradigm as to why we had started doing all of this and how this impacts us in a significant way, and where domain adaptation actually comes into a very practical world as a savior when trying to solve a lot of problems which we face in a day-to-day life, and it being a very practical thing to be used. So without like really spending a lot more of time, let's get deep into the topic. And as and it keeps on going, and I would try to answer down a few more questions which keep upcoming on the chat board while I keep on progressing with this. So now, as we all know that deep neural networks are not something which has come up new, although the surge has been somewhere around in 2010 onwards, with the world actually taking it up in a big way. And one of the reasons that we had this great surge in deep neural networks coming up around that time was that we have now computational infrastructure which makes it possible to train these kind of networks on, say, what is a desktop scale. Earlier to that, this was more of with HPCs, and you needed big scale infrastructures which were within the reach of very few labs in academia predominantly, and only a very few coveted organizations which were trying to encash on the spread about with data. Now, with this deep neural networks coming up and big data archiving, retrieval, and these kind of infrastructures helping actually the whole machine learning community in order to make a good use of this big data, they started growing up. And how it came down into existence was, on one side, we had this great exquisite theory on deep neural networks, starting from autoencoders to convolutional networks, from there to restricted Boltzmann machines to recurrent neural networks, and what today we have real gaga going around with LSTMs. We had all of them. Then we had these kind of new generation tagging mechanisms which came up into place and which became practical. So we had a lot of these e-commerce search coming up, which led to behavioral analytics and collecting data about buying behaviors and consumer purchase consumption behaviors coming up. Then we had geotags associated with all kinds of activities which we do. So today, when you are traveling anywhere, you tag your posts on Facebook. You are tagging your photographs, not just with people on those photographs, but you also tag them down as to where you have traveled. Then we had these new thing from Amazon as mechanical Turks, where you could actually hire down workers at very meager prices in order to do manual tagging. So if you wanted to tag down what objects were present on images and a large variety of images, then now you have an option of actually tagging them individually by using these Amazon mechanical Turks. And now this was a big treasure trove of data on which we were sitting down. On the other part of it, these GPUs, and with Google coming up with the TPUs, though I'm not quite sure about whether it would be more of it would ever be a proprietary or not. Now, at least these GPUs enabled us to get down these kind of HPC-like compute powers on our desktop skills. So today, typically what you have, say, with a 1080 Ti, which goes down something in the order of a few teraflops, in tens to 20s of teraflops. Now, that would help you have the compute power, which was, say if we look into the world at least 5 to 10 years ago, then that kind of a compute power would have meant that you have a few rack mounted servers kept down over there. Maybe a 16 node or a 20 node server would be giving you that kind of a compute power, and that was too costly. Now comparing the cost side of it, the 20 node server at that time, or even currently in Indian rupees, this would be costing down really in the order of at least a crore. And now we are looking into GPUs which cost you a 1080 Ti was basically barely be 60,000, 66,000 rupees or something of that sort. So this is a scale of difference which has come down, and that has led to with this hardware becoming really easily accessible is where our compute growths have happened. From there, we did have this lot of standard challenges and data sets come up, from MNIST being the first one on which CNNs were ever tried out, from there to CFAR, Street View House Numbers, ImageNet, and a lot of them. And what this led to was actually getting down onto a lot of practical developments. And these practical developments include mail sorters with the post offices department, postal departments across the world, more or less, including even in India, where you have automated mail processing centers in which make use of vision-based algorithms, and predominantly a lot of these convolutional algorithms in order to sort down and actually classify and categorize your mails or postal mails as to based on the destination pin code numbers, and they do it pretty good. From there to Facebook, which actually helped. So today what we have done was one of the biggest experiments and helping one of the biggest scientific experiments ever in the world. So this whole art of where it recognizes faces immediately without any much of a jitter or anything coming up. The ease thing was that when Facebook started initially coming up and they was letting people post photographs and then tag themselves in photographs. So we were inherently helping a whole vision-based system come up to the point of actually labeling out data. So we were labeling and providing them a lot of training data so that they could actually come up to a point where they can make a system which is really efficient to find out faces and identify individuals across any kind of images which goes. And this has immense application, not just in social media where you see it being used immediately, but this goes much beyond it into security and surveillance aspects as well. So from there, we continue on to self-driving cars, and then with autonomous driving today really being a buzzword. And we see that there are companies which are putting this into actual commercial trials on real roads with actual consumers trying to get into those cars and go out. So this is where deep learning and all the developments along with big data has really enabled the practical world to come up to that. And then you have this like really artistic one on Prisma, which is my personal favorite. And I always take this up, although it comes out as really a small thumbnail over here on the corner. The whole thing with Prisma is quite a beautiful thing, because this is where I can actually start telling about domain adaptation. So you had this kind of a hand-painted drawing from one of the artists, and now say you want to see your photograph being transformed into, and what would it be looking like if the same artist had painted. Now you take one of these images and then train a network which identifies and then can actually recreate stroke lines from actual object appearance models of some sort. Then you take the appearance model from here and then you merge it with the stroke lines, and then you are able to do it. So this is a perfect example of what I would say as domain adaptation. You don't have a knowledge about the other domain on which you are applying, but you can now try to actually adapt it between one to the other one. Now, this is quite fun to like really look into one of those experiments. Now, from there into where the kind of work I do and what it looks into. So where we are working today, so on deep learning, it has a lot of different market scenarios in which we look. And the work which we do at our lab over here is very specifically in the area of visual computing. And to be very specific, it's what's called as computer vision or machine vision. Now, if you look at that market for machine vision-based systems, and say somewhere in the year 2020, based on the surveys which we have, so about 37% of that market share itself is for one single distinct area, which is on medical image analysis. And if you put down the other areas over there, which are media, surveillance, automotive, graphics, so this includes media entertainment industry, then graphics in terms of what is being generated on your screens for say report presentations to this simple graphics being used for your PowerPoint presentations to even quite elaborate and animated graphics being used for demonstrating future scenario events or animating what it would be like life in space. So all of these together would be about $6 billion of a market at 63%. Now looking at this area on which is the area on which we specialize more or less on medical image analysis, where domain adaptation actually has a real big role to play, becoming the savior in order to bring down a lot of developments which we have done on lab scale scenarios to actual bedside practices. And where they would be impacting is these kind of developments would be impacting significantly in terms of leveraging a lot of image analytics problems for MR, microscopy and pathology, and X-rays, ultrasound, CT, and nuclear imaging. These would typically be used in the clinical indicator scales for radiology, cardiology, oncology, neurology, gynecology, and mammography. And what these clinical indicators basically mean is that what kind of clinical specializations and specialties would our developments of these sorts be impacting, and they are across filled almost across for all of them, although I don't have surgery and surgery over here. But then as we keep on going through it, we are seeing that there are certain developments which we would be bringing into bettering the whole process of surgery for the near future. And the end users would definitely be on the primary part of it, hospitals, and then eventually that would be extending onto diagnostic centers and research centers on a real big way. So where this whole problem starts is something of this sort. So say that we start with this whole simple problem. Let's keep it as a simple problem. So I have a deep neural network, and where I want to solve it out is, let's look into a semantic segmentation kind of problem perspective, in terms of trying to segment out different organs and different kinds of tissues in a MRI image. And this MRI image, what we have for segmentation is a T1 weighted. So that's basically a particular type of MR imaging done, and these are all MR images of the abdomen of a human. Now say I am training this neural network in order to work on MR images of the abdomen in humans and classify all different kinds of tissues. Now what I do is I have another bunch of images coming down which are MR images of the brain, and then can I use the same kind of a network in order to classify these MR images of the brain? And this is where the whole problem comes into it. Because one thing what you would see is that the nature of tissues which are present in hello? Oh, this just stopped, right? Uh, yeah, so till, is it coming up now? Okay, so that was quite weird until anyone actually told me out that we weren't transmitting the screen. Okay, so I would now try to be on a different mode. I will work it out from the instead of actually going on a full screen mode. Let me try to do it on a normal way. So I hope that works out good. Now that yeah, so this was the second slide on which I was mentioning to about these different kind of developments which have happened down over there, and then my personal favorite on this Prisma coming up over there. So this is the slide I was mentioning over there. So say that you have these T1 MR images coming up, and then from this T1 MR images, I have these approximate labeled anatomy available to me, and these are all different kinds of tissues which you would want to make your neural network actually learn. And then what the problem happens is that you train a big neural network using this huge amount of data of T1 MRI of this abdomen over there, and then what you want to do is that can you leverage the same amount of so whatever you have trained on this deep neural network after a good amount of data on in terms of labeled samples and also the raw images which you had together, and can you use this model directly to do a tissue labeling for your MRI images of the brain. Now where the problem comes in that in MRI images of the brain you actually don't have the same kind of tissues, neither do you have the same kind of organs. And the other point which changed was that this is a T2MR. Now for those of you who might be from medical imaging, it's easy, you can understand it. For others, let's keep it something like this, that whatever comes as dark in T1 will be coming as bright in T2, and then it might not necessarily be so there are different interests. So it's a different physics in which these two MR images are acquired. And now if we push this whole thing into this system, now that's obviously not going to work out. But the challenge is that in that case, what do we do? I mean, seriously, if I want to have a semantic segmentation for my whole human body, and it can be, I can, and I would try to run it, say, on CT, I would try to run it on MR, any particular modality on which I can get a whole body imaging being done over there. Now the problem comes into, if I try to do it only with this T1MR, then the method will not be working on T2MR. And say I train it for abdomen, then it will not be working for brain. Then what do I do? Should I be creating that many number of models? And that would definitely mean that I would need to get a lot of label data. And that's where the whole problem creeps into it, because getting that huge proportion of label data is actually not possible. And getting it in terms of, say, ImageNet is a much easier problem, because at least you have normal humans who can identify standard things which we see in natural images and then annotate them. But these are medical images. You would actually be needing experts, and these experts are not just say general physicians who can do it, but these experts are people who are radiologists, trained radiologists. Now they already don't find time to treat and diagnose enough number of people because of the already pre-existing workload. Now and here we are speaking about looking into asking them to actually annotate all of these images, and that's where the whole problem lies. So it's not possible, and that's where this whole thing comes into it. And I would break down the problem of this big data availability into a three quadrant rule, which we a three sector rule which we follow down. So in terms of if you look into machine vision and medical image analysis together, then one thing is the number of instances, and this number of instances is basically what would typically be called as number of samples in a majority of the cases. But here this number of instances is basically, say, one human is one instance, and number of times this human is being imaged is a different sample per instance. So that's how it goes on. So for machine vision problems, typically the number of instances is very high. So the number, and then for medical image analysis, the number of instances is very low. Whereas if you look into the last part of it, which is sample per instance, you would see that in machine vision, say 1% is not imaged a lot of times, but number of parts of a human being which is imaged in medical image analysis is very high. And typically, say for a MR imaging, say a whole body MR image would have about something like 500 to 4,000 slices. And what that means is that your body is being dissected on the digital side of it into that many small number of 2D image frames coming down. So for a standard camera image, your image is just your image. Maybe like you are taking an image of yours from 2-3 different sides, or maybe 100 different angles at most, not more than that. And here we are speaking about 4,000 such slices coming down every time you enter into the machine. So the number of samples per instance is very high over here, whereas the number of instances is pretty low. And on the other, so if you look into something like a product of number of instances and number of samples, that would be more or less same for machine vision and medical image analysis. But this is where the disparity rises. The other part is that number of annotations per instance, and what this means is that whether each instance is completely annotated or it's not completely. So for all machine vision tasks, generally scenes can be annotated completely. And today we have those kind of large data sets which have all of them. But for medical image analysis, it's really hard. And given the fact that if you want to exhaustively annotate the complete instance, which means that annotating each sample within each of these instances, and that would typically mean that you would have to employ a large number of radiologists in order to do all of them. And that's not a solvable problem. And standing on these problems is where we need to really invent onto how can we use a traditional knowledge with the techniques which we have today in place and take all of them together in order to build something much better. And once we are, say, able to solve all of them, what we are looking at is to look into developing something which is called as operating rooms of the future, where you will be having these kind of deep learning systems which will help surgeons guide them into how to operate much precisely. So there's a lot of technology which goes into it, and not just deep learning. So there is visualization technology, augmented reality, projections, and all of these which will together help people come up with techniques which would be much better for treating and diagnostics and treatment of people as we see today. Now, without spending much of the time on that, how I'm going to speak in details over here is to try to demystify this problem of what is called as a domain and then the domain adaptation, come down to its origin and a few notations, and then move on to classical approaches into what domain adaptation is and visual domain adaptation problems, and where people have been trying to solve them and what they have achieved by solving it out, if they have been able to solve it out. And then I would get into some of these application scenarios and speak of application scenarios in terms of whatever we have been able to solve till date, and then speak briefly about our experiences with generative models, with adversarial autoencoders, which also have a real big ability of doing domain adaptation within them. So the challenge, so this is where I believe anyone remembers this paper. This was one of the early papers which we had done of trying to use a hybrid architecture for deep learning. And the whole thing was that we wanted to do segmentation of retinal vessels and whether these retinal vessels can be segmented in a good way or not. Now, where the problem came in was that we tried to really pull it out into a different domain. And what that meant was these original images on which the whole network was trained was taken down from Drive. And these images were all of healthy individuals for whom we wanted to get the vessel segmentation done. And so for each of these images coming down, we had a map on which every single pixel which belonged to the vessel on the retina was completely marked down, and we trained down a neural network. And then based on that, given a particular test image coming down from the same data set, we had a very good way of detecting all the vessels perfectly. Now, where we wanted to really go deeper was that can we use the same kind of a network in order to do this vessel detection in those kind of symptomatic patients on whom this is actually needed. So this vessel detection problem is not something which you would do for healthy people as such. So this is typically done for people who have diabetic problems, and a very specific case of a retinal disorder called as diabetic retinopathy. Now, in those kind of situations only we will be trying to do it, because there a typical standard procedure of retinal angiography, which is conventionally used, cannot be used any further, because what you do in that is you inject a part of some sort of a fluorescent dye into the bloodstream, and as this fluorescent dye goes with your blood, so it starts to fluoresce, which is at a particular wavelength of, at a particular color of light, it would be shining into a different color. And now if you can filter out that color of the light, then you can see from where the blood has gone. And since blood is supposed to flow within blood vessels, so tracking down this whole path in which blood, this say fluorescing blood has been flowing down, so you can actually track down the whole blood vessel architecture over there. Now, these kind of dyes are basically toxic to people, and if you're a healthy person, you don't have an issue that you can pass down about say 2 or 3 liters of urine in 2 hours of time, and this whole thing flushes out of your body, and you are good to go with it. It's not that toxic to your body. But then if you are diabetic and we ask you that in order to flush this whole thing from your body, you have to really drink that much of water and do it. So this becomes life-threatening for diabetic people who already risk a kidney failure case as such. So there they cannot do this retinal angiography, but they really want to look into these blood vessels, because that's an indicator of where the pathology is existing with respect to them. And now when we try to deploy this whole network, which was trained on a large corpus of images from healthy humans, it really failed, because all of these white spots which you see over there, they're all on the background, but then white over here is just a classification label associated with the presence of blood vessels, and this is where the whole method fails. Now, with this problem in hand is when we started getting into the whole aspect of deep learning, and that's where we wanted to see it. Now, in order to get deeper into it, the idea was, let's try to demystify as to why was this whole issue coming up over there. Now, as we went into it, what we saw was that there was a distinct shift in distribution of the color elements in each of these images. And where this shift was coming was something of a sort that, say, in if you look into this drive image and the steer image, then we did a very simple experiment, and that was just to look into the histogram of red channel, green channel, and blue channel of the pixels in each of these images for the vessel class. Now, the solid line is what is there for the drive dataset, which we call as the source domain. So this is the set or the domain of samples on which the model is initially trained, and then the dotted lines are from the target domain, which is the domain where we would like to deploy our model in. And now when we see over there, we see that in the drive data set, you have some sort of an overlap between each of these domains, and that's not so hard to find. And in the green channel over there, you have much lesser overlap, maybe a 30% overlap similarity between these two distributions over there. But if you look into the blue channel, you see that there is no overlap, and one is quite different from the other. And this is where the whole problem creeps into it, because now that you have a distinct domain shift coming down, the whole method is deemed to flop and fail down over there. But the question is that on my steer dataset, which is for my diabetic patients, we don't have an option of getting down these ground truths, because we cannot do an angiography. The only other option is that we make a ophthalmologist sit down over there and keep on manually annotating. And this would bring us to another problem that, say, today I am imaging this with one particular kind of a camera sensor and one particular kind of a microscope. Now, if I change this kind of the sensor and the microscope, then do I need to again create another network, and which is trained with a large corpus of new data coming into it? And if that keeps on going like that, which means that every time I have a new fundus microscope come in, and every time I have a new camera sensor being used with the fundus microscope, I will have to again recalibrate my system and train the whole model once again completely from scratch using new data coming. And this is not a engineering feasible problem in any way. So that means that every time I have a new camera coming, let me again try to retrain my analytics algorithms. And so that means that the reach of a hardware to the market will heavily get dependent on softwares, and whether these softwares are perfectly working or not. And that never is a feasible solution. So that's where the idea of domain adaptation comes into it, and there's a very simple thing which we tried doing. So okay, so sorry for that weird interruption again that we lost in between. I will again go over here with this one. So here the idea was that we have this large corpus of images from the source domain, which was the drive data set taken down on healthy patients. And these were, although this in a simple terms, it's just 40 images which you have annotated and which you can be using. But then from the medical perspective, 40 images is actually a large corpus of images. It's not a very small thing. Now we have these 40 images taken down, and then we put it into the neural network and we can train it out. And now the point is that if I want to really use the knowledge which we have gained down from having 40 healthy person images to using them for diabetic retinopathy patients, then what do we do? So the idea was that we can acquire one image and get it annotated for all the pixels over there, and then use this to retrain or try to adapt the whole neural network, such that when we give a new sample from the target domain coming into it, then we can get on a fairly good prediction for this image over there. And what essentially that means in terms of the parlance is that say I am looking at a joint probability distribution space in my source domain. So I will be having a lot of samples on my positive and negative classes over there. And the whole objective of domain adaptation is to somehow shift this classifier margin to my target domain such that I can have a much better quality fit over there. Because if you look into the target domain data distribution, because the number of samples in target domain is pretty low, so I exactly don't know where, if I am trying to train a whole classifier on the target domain with this less number of data, so I might not always be getting down a perfect fit. So then I can get down a line something like this, I can get down a line like this, and not all of those lines would be something which would be generalizable over a large number of samples in the target domain. So that's where domain adaptation actually plays a significant role in bringing a feasible solution. So if we look into the history of domain adaptation, then you would see that these methods, they range across multiple of them, and the first one of them, which is quite famous, is called as feature augmentation, in which the idea is that you transform a feature space which is in a lower dimension to a much higher dimensional space, in which this sort of a transformation would induce some sort of so you would be adding some more sort of zeros over there. So this is like you're transforming onto a higher dimensional space, and all features would lie down on one single sort of a hyperplane itself on a higher dimensional space, such that if we look at this transformation from the source domains to this higher dimensional space, then wherever this plane on which it is lying down should be same as transforming something from a target domain to that higher dimensional space, where both of them merge on the same plane. Now with this one, as the planes would also be merging, so your classifier margin would also be coming down onto a common conformal origin. And now I can, if I know what is my transformation on my feature space, so obviously, since any kind of a classifier is basically a linear algebra operation, or this yeah. So with this thing on feature transformation, the whole idea is that we would like to move from a source domain to target domain in a way such that while I'm moving from the source domain to the target domain, I would be moving via some sort of a manifold. Now, for those of you who are not quite aware of what this manifold as a concept means, is this gets its name from a structure which has fold within folds. So if you had looked into those old age Victorian era movies, say like Pirates of the Caribbean, you would have the nobility and noble people going on with locks of hair, and that's what is typically a manifold structure. Now the whole thing of a manifold is that as we want to transverse from one point to another point, which is the path linking down these points, now in a free space, this path linking down the point can exist in any part of the space, and all points and any point on space can be tracked back to a particular path over there. Now for a manifold, the problem comes in that this cannot just be any path existing in space. This has to lie along that surface itself, and any kind of a traversal you want to do along that path, you will have to traverse along the surface of the manifold itself. Now, with that problem in hand, and what this defines is that if we can define some sort of a manifold on which a path can exist from the source domain to the target domain, then as we traverse, we would be touching down on all different kinds of transformation of going down from one to the other, and that's where it makes it much easier to work it out. So from there, we have another model which is called as a dictionary learning based system, and this is one of my personal favorite one, where what you do is that, say you want to learn to classify bags from human faces, but what you also want the system to be able to do is, say it can be a photograph of a bag, it can be a sketch art of a bag, it can be a thumbnail cartoonish kind of an image of a bag, and you can have the frontal face of an image, you can have the of a person, you can have the side view face image of a person, you can have a hand sketched face image of a person. Now you have to really distinguish between them. So whether it's a bag or it's a face of a human. Now how do you do that? Because generally, for whatever data sets you get, you would have normal images, or you would have sketch arts and pencil arts and handwritten drawings, handmade drawings over there. Now, for this, what the authors for this particular paper from Maryland had done was quite simple. So the point was to create some sort of a shared discriminative dictionary, and what that means is, say I put down all bag images into one container within a dictionary, and all face images into another container, and similarly for all other classes of objects which I do. So irrespective of the nature in which the image was taken, so it's just all different kinds of ways in which an image can be drawn or taken down, and you put it into one single bag, and then you keep on classifying. Now this is a very intuitively good way of doing adaptation with dictionaries. The only downside is that this cannot do a model adaptation, which is, say that today I have trained a model